Hi everyone, and welcome to the fifth online lecture for this course. Today we're going to be covering a topic from section 6.6 in the book called Integration by Substitution. And this is going to be probably the last of the more theoretical lectures that I'll be making in this course. From now on, we're going to be mostly focusing on applications. But this is an important topic. This is basically the one advanced technique that we're going to need in order to calculate integrals. And I think that this is a topic which is best explained by example. So let's jump into an example, and let's say that I asked you guys to find the integral of 2x e to the x squared dx. Now, the first thing that you would note over here is that this is not a simple, put in quotes, integral. That can be immediately solved with the rules that we learned in last lecture. So the reason for this is twofold. So first off, one reason is that in the exponent of our e over here, we have an x squared, not just an x. And when we covered our exponential rule for integrals, we saw that it worked for only e to the power x, or e to just a simple variable, whatever your simple variable is. And we don't have any rules that tell us how to deal with something like e to the power x squared or e to some more strange power. So that's the first thing that we notice is an issue. The second thing that we notice is an issue is this 2x in front. The 2 isn't a problem, but the x definitely is. Now the reason why this is an issue is that although we know how to multiply by constants and we know how to add, we do not know how to multiply two different functions together. So with just the basic rules that we covered previously, this is not a problem that at first glance seems to be possible. The technique that we're going to cover today, called integration by substitution, which basically, for the record, amounts to reversing the chain rule, although I'll get to that later, allows us to solve problems like these. And we're going to have a pretty straightforward strategy here. Our strategy here is going to be to use smart substitutions in order to turn this into a simple, in quotes, integral. That's going to be our goal. This is the main idea of integration by substitution. This looks too complicated for us to be able to tackle with the rules that we know. So let's see if we can do some very straightforward algebraic substitutions and get it to look like something much simpler. Okay. At this point, the question becomes, how do we do this? And is there a way that we can attack this properly? Let's break this apart step by step. And step 1 of integration by substitution is to look for an inside function, and I mean inside function in the same way as I use the term inside when I talk about chain rule. But you specifically want one whose derivative shows up outside. And in this case, I've already colored these in for you. The inside function you can see is going to be x squared. And note that 2x is the derivative of x squared and shows up outside. And this leads us directly into step 2. Give the inside function a name. Now you can give it any name that you want. You can call it Bob, you can call it Jim, you can call it Catherine. But I usually just stick with the letter U. The book, I believe, likes to use the letter W. So let's call this U. I'm going to do this in blue. And we're going to have that be x squared. All right, step 3. Is find du dx. I'm going to color this. Going to color this one in green. You see that du dx is equal to 2x. Now note that if du dx is equal to 2x, then du is equal to 2x times dx. And this isn't exactly a multiplication, but you can think about this as multiplying on both sides by dx. That's not exactly what's going on, but it's close enough. And it's not something that you guys should worry about. Okay, so these are the first couple of steps that we're going to be doing. In order to do a substitution, we have to figure out what substitution we're making. And the substitution goes as follows. You find what substitution you need to make by looking for an inside function whose derivative shows up outside. You give this inside function a name, and then you find its derivative. I almost always in this course will use the letter u for my substitution, and then its derivative will be du dx, and specifically you're looking for u, which will be the derivative of u, you're looking for du, which will be the derivative of u times dx. Okay. This leads to step 4. Step 4 is very important. You need to replace all, and I do mean every single instance, of x and dx with u and du. If your variable isn't x but is, say, t, then you need to replace all of the t's. The point is, all of your old variables, all of them need to go. So let's do that now. In this case, we see that this integral will be equal to, now the integral of, let me get the right color here, we're going to have e to the u up here times du. And the reason for that is that this 2x dx becomes du, and this x squared becomes u. Okay, once you've done this, it turns out, and this is where this method gets to be a little bit trial and error, is that if you've chosen the correct substitution to use here, then step 5 is just integrate. And in this case, we can do this just fine. The integral of e to the u du, same thing as the integral of e to the x dx, or whatever. We have the integral of e to our power, our variable power, d variable, is just going to be e to the u plus c. And you can see here, remember the goal of this process was to use a substitution to transform a difficult problem. Remember, this was hard, into an easy problem. This one is easy. This is literally just our exponential rule for integrals. All right, we're not quite done yet, though. We still need to do step 6. Swap back to the original variables. And in this case, we'll see that this is going to give us e to the x squared plus c. So by using our substitution method, we've been able to determine that the integral of 2x e to the x squared dx is e to the x squared plus c. Okay. This is a really useful method. It's a very powerful method. It's something that is going to be used all the time if you do any integrals with any sort of regularity. It's the only advanced method. There are other advanced methods for integrals. This is the only one that we cover in this class, so you don't have to worry about all the other ones. And there's just a quick sort of remark to make here before I move on, is that the substitution method basically amounts to undoing a derivative that was obtained with chain rule. And you can just double check this, because remember that derivatives and integrals are the opposite processes of one another. And you can check that, for example, e to the x squared, if you were to take its derivative, you would have to use chain rule, and you would get that its derivative is 2x e to the x squared. So whenever you're basically undoing a derivative that was obtained with chain rule, that's when integration by substitution is going to come into play. But again, that's sort of on the theoretical side. You don't need to be thinking about chain rules and all of that stuff in order to do integration by substitution. You only need to follow these 6 steps that I have written out here on this board. And that should get you where you need to be. Okay, so what I'm going to do now is I'm going to sort of rearrange these steps as I've written them here, and then we're going to attack another example. Okay, so first things first, let's erase all the specific details about that one problem. Okay, and next, let's do another reminder here that our du is going to be equal to du dx times dx. Okay, let's rearrange this a bit to make this more clearly visible. So we have our 6 steps. Step 1, look for an inside function whose derivative shows up outside. Step 2, give that inside function a name. Step 3, remember I usually like to use u as the name, which means that step 3 is going to be to find du dx. But in general, it's find the derivative of that inside function. And then find specifically what du is going to be equal to. And that's just that derivative times dx. Step 4, replace all x's and dx's. Every single one of them needs to go. Replace them all with u's and du's. Step 5, just integrate. Remember, if you've done this correctly, if you've chosen the correct substitution, by the time you hit step 5, the problem should now look like a very, very easy and straightforward integral. And step 6, of course, is to swap back to your original variables. Okay, I'm now going to leave these steps up here on the board so you can refer back to them. And while I do that, I'm going to tackle another example. I want to point out at this point that I will be making another example problems video going over this technique of integration by substitution more in depth and going over more examples. But what I'm trying to do in this video today is try to make it clear what the idea is, what the process is, so that when I tackle examples in a later video, you don't have to think about that too much, and you can just focus on what the procedure is. And there's a specific point I'm hoping to make with this next example. Let's say that you are tasked with finding the integral of the square root of x cubed minus, let's say, 2 times x squared dx. Okay, step 1. Look for an inside function whose derivative shows up on the outside. Now, clearly the inside function in this case is going to be x cubed minus 2. And when you look for its derivative outside, we can find an x squared, which seems to be the derivative of x cubed minus 2, but we're off by a little bit. Now, we're going to come back to that later. Don't worry about that for now. So the first thing to do is that we're going to say u. Let's let that be equal to x cubed minus 2. Keep in mind, we need the minus 2 in here as well. In my experience, students often just see this problem and let u be equal to x cubed. You need to capture the minus 2 as well, because you need to get everything that's in the inside function here. Okay. So that's steps 1 and 2, I should actually say. Let's move on to step 3. Step 3 is finding du dx. And remember that to do this, you're not looking in the integral that you're asked. You do not look, you do not fetch this somewhere. You find du dx by computing it based on what u is. Du dx is equal to the derivative of x cubed minus 2, which is 3x squared. Now this means that du is equal to 3x squared dx. Okay. Now this is a point where we get a problem that I want to address here. In green in this integral up here, you'll notice that we only have x squared dx. So we only have this part. We're off by a constant. And the point I'm trying to make with this example is that if your du is just off by a constant, you're still okay. If it's off by anything else other than just a constant, you have a problem. If it's off by a constant, you are okay. Why is this? Well, we can do the following step. Note that now, if we have x squared dx, like we have up in our problem, this is going to be equal to du over 3. And this is a really important, I'm going to circle this in red, this is a very important little trick to do. If you're off by a constant, you can shift it over to du. This is okay. Once again, I want to repeat this. I need to be very, very clear about this. If your du is off by more than just a constant, you have a problem. Your substitution will not work. If your du is just off by a constant, then you are okay. You can just shift that constant over. Okay, let's see what this looks like in action. I'll make this a little bit smaller as I attack step 4. extend this line a little bit. Step 4. Remember, we need to now swap out all of the x's and all of the dx's with u's and du's. What do we get? We still have the integral sign, and we still have the square root. But now under the square root is just u. And then we have a du over 3 here. Okay, we can shift, remember, constant multiples, and this is the reason why being off by a constant is okay. Constant multiples can be pulled out of the integral. So we can take this 1/3 and pull it out in front and be left with 1/3 times the integral of square root of u du. And at this point, double check, make sure you still don't have any x's left and all you have are u's, and you can see we've successfully swapped everything out. All right, step number 5 is to integrate. Okay, so remember the 1/3 is going to stay there, and now we have the integral of square root of u. Remember, square root is just the power 1/2. So we're going to use the power rule here. We're going to get u to the power 1/2 plus 1 is 3/2. And in front, we're going to divide by this new power, which will give us 2/3. And don't forget your plus c. How did I do this? This is just a power rule. Okay. Last but not least, step number 6. We need to swap back to our original variables. So at this point, we have 1/3 times 2/3 times u, which is being raised to the power 3/2, plus c. But our u, we stated at the very beginning, is equal to x cubed minus 2. And this is the final answer. This is the value of our integral. Okay. So once again, I am very aware that this is not the most obvious process. In my opinion, this is the hardest of the advanced techniques that we see for either derivatives or integrals. Of all of them, I think this is the most difficult. I highly suggest that you practice this a lot. There will be a homework set involving this that I'll probably assign after the exam next week. So don't worry about this for the exam next week. This will not be on there. I want to make that very clear. This will be on the final. I'll give you guys a homework set that basically focuses on this, and I think the best way to learn this is to practice, practice, practice. Also, I just want to remind you guys, I will be doing an example problems video focusing on this method as well to hopefully help you guys a little bit more. I'm aware this is difficult, but this is an important method, and hopefully you guys can see what the purpose of this all is once you get to this step here. So once you get to step 4, as you can see, just as in the previous example, this integral looks really easy, right? This is just a power rule. And that's the goal of this method. At the end of the day, the goal of integration by substitution is to turn a difficult looking problem, like this integral of the square root of x cubed minus 2 times x squared dx, that looks like a bit of a mess. The goal of integration by substitution is to make your life look a lot easier. Give the ugly looking stuff a name, just call it u, replace it all, and you should hopefully end up with something that looks a lot nicer. That's our goal, and that's what we're trying to do with this method. Okay, with all of that said, there's one more example I want to cover today. And that is how to do this when you have a definite integral that you're trying to evaluate. So this will be sort of my closing example for the day. Let's say that you're trying to find the integral of, let's say, t e to the t squared plus 1. And let's evaluate this integral from 0 to 3. Don't forget the dt. Okay. So we're going to tackle this just like any other definite integration problem. Now in the book, I want to mention that the book gives you a way of being able to tackle these while swapping out the limits of integration and stuff like that. You can do that if you want, but I don't think that that's necessary. I won't dock you any points for doing that if you feel like it, but you don't need to do any of that to do this. All you have to do is first do these 6 steps that I've explained here, and then plug in the limits of integration. So this would add just a step 7. Step 7. This is for definite integrals. Punch in your limits. That's all there is to it. We're just adding the extra step like we do for any other definite integration problems. So first, find the indefinite integral of t e to the t squared plus 1 dt. Okay. Let's do this step by step as usual. The first thing to look for is going to be for an inside function, which we can see in this case, your sniffer that you should have hopefully developed from chain rule to try to locate inside functions should help you out here. And it should be telling you that this t squared plus 1 looks like an inside function. And a quick double check, does its derivative show up on the outside? Well, we do have this t here, and that should help us out. Okay, so step 1/2. You see we're going to set u to be equal to t squared plus 1. Now step 3, we need to find du. And du is going to be equal to the derivative of t squared plus 1 is going to be 2t times dx. Okay, once again, you can see that we're off by a constant. And if you're just off by a constant, you are okay. Remember, off by a constant is fine. More than a constant is not. So here we're going to see that we need to find t dx, and that's going to be equal to du over 2. Okay. Step number 4. Let's replace all of those t's with our u's. We now have an integral of e to the u times du over 2. And let's rewrite this to pull that 1/2 out in front. It's going to be 1/2 integral of e to the u du. And remember, the whole idea of this method is at this point, at step number 4, to hopefully have a problem that looks much easier. And that's what we have here. Integral of e to the u du is very, very easy. Okay, that leads us to step 5. Integrate this. Integral of e to the u is just e to the u. Don't forget the 1/2 in front. And there's a plus c here, but since we are in definite integration, remember the plus c does not matter much for definite integrals. Step number 6. Actually, let me go back and write this u in color. Step number 6 is to swap back to your original variables. So we now have 1/2 of e to the u, which was t squared plus 1. And again, we have a plus c here, but I'm putting this in parentheses. Okay. Let's make this a little bit smaller to do our very last step. Our last step is to go back to the original definite integration problem and to punch in the limits. So now we see that the integral of from 0 to 3 of t e to the t squared plus 1 dt, this is going to be equal to 1/2 e to the t squared plus 1. And we're going to be plugging in the two limits of integration from 0 to 3. And if we write this out, we're going to get 1/2 of e to the 3 squared is 9 plus 1 is 10, minus 1/2 of e to the 0 squared plus 1 is e to the 1. Okay, that's all there is to it, nothing fancy. First, do the indefinite integral problem using the 6 steps I've written over here. And if you have a definite integral, at step 7, go back to the limits of integration, punch those into whatever you got as the result of the indefinite integral, like you would for any other definite integration problem, and you will be good. Okay, that's about it for this lecture. First, just a couple reminders. First off, this is not going to be on your exam for next week, so don't worry about this. Also, this is probably going to have been the last of the theoretical lectures for this course. So basically everything we cover from now on should be mostly just applications and that type of stuff, which hopefully will be pretty nice. And also remember that by the time of the final, I will have put out for sure a practice example problems video out on these, going more in depth in attacking lots of different types of problems using this method. Hopefully this lecture gives you an idea of what this is doing, of why we're doing it, and what the general steps to follow, and I can build off of those in that next video. Alright, that's all I've got for you guys today. I hope that you guys are staying safe and healthy at home, and I'll see you guys in the next video. Bye-bye.